All right, let's take a look at example 3 and example 4. We're on page 124 in section 4.4, continuing with quadratic models from verbal descriptions. Here we're going to look to maximize the area enclosed by a fence. So we assume David has 400 yards of fencing and wishes to enclose a rectangular area. So if I look at that, I say, alrighty, he has a rectangular area, it has a certain width and a length. And I'm going to flip my iPad so it's a little bit easier to see. So we know he has 400 yards of fencing total, so that means that the perimeter, if I were to walk all the way around it, that's going to have to be a max of 400 yards, right? So that means that the perimeter is equal to 400 yards, which is equal to 2 times the width plus 2 times the length. I can simplify that a little bit real quick here and say that that means that 200 yards gives me halfway around. So 200 yards equals the width times the length. So let's leave that there. If I were to walk halfway around, I'm going to have walked 200 yards. He wishes to enclose a rectangular area, we said already. We want to express the area of the rectangle. We want A as a function of the width, so we want A as a function of W of the rectangle. And coming back over here, we know that the area is equal to the length times the width for a rectangle. So if we're looking to find the area as a function of the width, then we can substitute in, if we know the width up here, if we can find the length as a function of the width. So let's start with that. So if we subtract W from both sides here, then we'll get that, let's move this A equals length times width down in a second. Let's move it over here. Equals length times width, just so that we know that. That's a formula we know. So here we know then that 200 minus W equals the length, which makes sense. Halfway around is 200. If I walk the width of it and take it off, then what's left is the length. So if I go back and I want to get the area in terms of W, I can say it's length times width. I know the length in terms of W, so it's 200 minus W times W. So this right here is the length. So that means I have 200 W minus W squared, and that's going to be my A of W. So let's write it down here nicely. Equals negative W squared plus 200 W. It's kind of a more standard form. So that's the end of part A. Part B asks for what value of W is the area largest, and you should be thinking maximum here. So when you see largest, you're thinking maximum. And we note that if we look at our A of W equation, that A equals negative 1, which is less than 0, so that means that we're concave downward. That means that we have a maximum at the vertex. So our maximum, we want to know what W is area largest, so we want to find W equals what? When the area is the largest, and we know the largest area is going to happen at the vertex. When A is largest. So let's find what the vertex is of our A of W equation. We know that A of W is equal to negative W squared plus 200 times the width, the W. So that means that our vertex, remember, which is our maximum, is at B over negative 2A. and in this case, a of b over negative 2a. And remember, this is my max width, or my width when it's max. Let's read it that way. This is my W at the max, and this is my area at the max. So if I find W equal to B over negative 2A, I have, in this case, B is 200, negative 2, and A is just a negative 1, so I have 200 over 2, which is going to be 100. And in this case, we have W equals 100 yards, because that's what our units were. So that's the value of W when the area is largest. The next section wants to know what is the maximum area. Max area equals what? We know again the maximum area we saw right up here is the area at the max is going to be at the vertex. So we just found that the width when it's maximum is 100 yards. So here all we need to do is substitute A of 100, which is going to be negative 100 squared plus 200 times 100, which should come out to be negative 10,000 plus 20,000 which is going to be 10,000. And this is going to be 10,000 yards squared is my maximum area. All right, so that is the answer for part B or C here, and that is the end of problem 3. Let's go ahead and take a look at problem 4. Here we're going to look at a suspension bridge. So we have a suspension bridge with a weight uniformly distributed along its length. It has 10 twin towers that extend 75 meters above the road surface. So I have 2 towers. Here's tower 1 and here's tower 2. They're going to extend 75 meters above the surface, so they're 75 meters tall above the road between them. Okay. They're 400 meters apart, so this distance is 400 meters. Let's put meters on there. All right, 400 meters apart. The cables are parabolic in shape, so they look like a quadratic. Okay. And are suspended from the tops of the towers. The cables touch the road surface at the center of the bridge, so right here at the center at 200 meters on each side. We're going to go up, and we're going to go up. We want to find the cables at a point 100 meters from the center. So we want to find, this is going to be our 200 point. On each side. Let's do this a little bit different. This here to here is 200 meters. All right, and we're assuming that the road is level. So let's start. Here, we're going to draw a line straight up and down, and we're going to put our center so that this is our x, and this is our we'll call it h of x for height. is going to, our origin is going to be right here in the center because it's a nice 0, 0 point. So here we're going to say we have a vertex that's at 0, 0, which is also equal to HK. Alrighty. And we have a point. We know already that we have 2 points, one here and one here. And this point is going to be 200 feet this way, right? Or meters, sorry, not feet. So it's going to be at x equals 200, and we know it's 75 meters tall. And we also happen to have one over here that's at negative 200 and also 75 meters tall. So we can use the formula that we found right at the very end of the last one where we put our quadratic into vertex form. If you remember that one, vertex form was f of x is equal to a times x minus h squared plus k. We did that right in the first video that I've done for this section, or for this group. And here we have the vertex, and we also have a point, right, that's at 275. Alrighty, so we have a vertex and a point, so we want to use the vertex form. So if we substitute in our vertex, we can say a is equal to x minus 0 squared plus 0, which is equal to ax squared. Makes it for an easy equation. So that's our height equation. Now if we want to find the a value, we know our point, so we can say, let's change this from an f to an h, like I have over there. We can say that the height at 200 is equal to 75. This is from the point, and that's equal to some a times x squared, which in this case is equal to a times, we know our x value is 200 squared. So here we have 75 equals 40,000 times a. So if I divide both sides by 40,000, then I can simplify just a little bit, and I end up with a equals 3. They're both divisible by 25 divided by 1,600. So my expression is going to be h of x is equal to 3 over 1,600 x squared. Right, so I have an expression now for this. What I want to find is the height of the cables at a point 100 meters from the center. So I want to know when x equals 100 meters, h of x equals what? So here, we're just going to substitute in. We have h of 100 is equal to 3 times 1,600 times 100 squared. And that means we have 3 over 1,600 is equal to 10,000. There we go. And if we put that into our calculators, then I didn't do that part, times 10,000 and 1,600. I'm going to come up with the height is right around 18.75 meters. And that's going to be the answer for the question. So when we are 100 meters from the center, the cable is 18.75 meters above the road. And that sums that one up. So I think we are good to go on that one.